Here we go. Let's take a look at something called piecewise functions. And to get an idea of what that's all about, let's take a look at an example. Suppose we have this situation. A city parking lot uses the following rules to calculate parking fees. We have a flat rate of $5 for any amount of time up to and including the first hour. We have a flat rate of $12.50 for any amount of time over 1 hour and up to and including 2 hours. And lastly, we have a flat rate of $13 plus $3 per hour for each hour after 2 hours. So what would happen if we parked in this parking lot for, say, 30 minutes, a half an hour that is? Well, we'd have to pay $5 because 30 minutes is within the first hour, and we know that for that entire first hour, we're looking at a flat rate of $5. Similarly, if we were in the parking lot for 45 minutes, well, that's still within that first hour, so we'd only have to pay $5. Even if we were in the parking lot for exactly 1 hour, we're paying $5 because this $5 flat rate includes everything up to that first hour. Now, as soon as we go over an hour, we're looking at a different price. So, for example, say we parked in the parking lot for 1 hour and 10 minutes. Well, now we're going to have to pay $12.50. Right? And that's all the way up to 2 hours and including 2 hours. So if we're in the parking lot for 1 hour and 45 minutes, we're paying $12.50. If we're in the parking lot for exactly 2 hours, we're paying $12.50. Now, once we go over 2 hours, things get a little more interesting. Let's say we parked in the parking lot for 3 hours. Well, at this point, we're talking about a flat rate of $13 plus $3 for each hour after 2 hours. Now, if we're there for 3 hours, that's 1 more hour than 2 hours. So we're going to have to pay this extra $3 on top of that flat rate of $13. So for 3 hours, we're going to be paying $16. Okay, let's move on here. What do you think a graph of cost versus time would look like for this situation? Well, you can pause the video here and try to draw your own graph, and you can probably imagine it's going to involve several pieces because we have several different rules. We have a flat rate of $5 that goes to a flat rate of $12.50 that then changes to a flat rate of $13 plus $3 per hour. Here's what the graph looks like. Notice we do have several pieces, and we'll just take a look at each piece here. If we park for 0 hours, we pay $0. Now, from 0 hours to 1 hour, we are paying our flat rate of $5. So even if we park for just a half an hour, we're still paying $5. Now I'll draw your attention to this. Why is there an open circle here? Well, for 0 hours in the parking lot, we're paying $0. We're not paying $5. So we indicate this by putting a solid dot at 0, and we use this open circle up at 5 to say we're only counting this line segment as part of our graph after 0, not at 0. From 1 hour to 2 hours in the parking lot, we have a flat rate of $12.50. Now again, for 1 hour, we pay $5. That's why there's a solid dot there. We do not pay $12.50 for 1 hour. But after 1 hour, this is the function, this is the line segment we're using. And for 2 hours, that's where things got interesting. Now we know for 2 hours, we're still paying that $12.50 flat rate because that's up to and including 2 hours. But after that, we switch to a flat rate of $13. That's what this open circle here is indicating. And then each additional hour is another $3. That's why we're at $13 here, but by the time we get to 3 hours, we're up at $16. 4 hours, another $3, so we're at $19. 5 hours, another $3, so we're at $22. A few notes about this graph. First of all, notice that the domain is all of the real numbers x such that x is greater than or equal to 0. Our x-axis is measuring time here, so our lowest value is 0, and we're looking at the values that are greater than 0. That is positive values. Notice this function is linear over its domain. We see a lot of lines. We see this line here that has a slope of 3. We see this line segment here, this horizontal one, this one here as well, all linear. And I guess we could kind of consider this tiny little dot here to be part of a linear function too. I mean, it's only 1 point, so I guess we could say that it's a single point on a linear function. The function is discontinuous at x equals 0, 1, and 2. Yeah, notice at 0, we have a jump from here to here. At 1, we have that same thing. We have a jump from 5 to 1250. And at 2 hours, we have a jump from 1250 to 13. So we do have discontinuities there. Those are the breaks in the graph. And we've already mentioned this. Notice the use of the solid and open dots to display whether or not the value is included. Okay, an open circle or a hollow dot indicates that that value there is not included. Everything after it is, though. And a solid dot indicates that that point or that value is included. All right, so what you just saw there was a piecewise function. And I think it should be pretty obvious as to why we call it a piecewise function, because it consists of several pieces. In the last example there, those pieces were all lines of some sort, or that single point. So what is a piecewise function? It's a function that is defined by using different rules on different intervals. Here's an example. And this might look a little bit intimidating, but don't fear, we'll talk about it and do some examples as we go through this video. First of all, notice we're saying we have a function called f, and it uses x as its input, so f at x, and you can think of this as being y. What does y or f at x equal? Well, sometimes it equals x squared, sometimes it equals x plus 2. So we have two different functions. You can think of it as we have y equals x squared, and we have y equals x plus 2. Of course, x squared is a parabola, and x plus 2 is going to give us a line or a linear function. The question becomes, when are we using each of those functions? And that's what this is all about here. That tells us when to use those functions. So when are we using the function y equals x squared? When the x values are less than or equal to 0. So as long as you're using x values that are 0 or less, we are using the function y equals x squared, or f at x equals x squared. Once you go past x values of 0, so x values that are greater than 0, we're now switching to this linear function y equals x plus 2. All right, and we'll soon see what graphs of these things look like. But all that's saying is, yeah, sometimes f at x is x squared, sometimes it's x plus 2. When is it each of these? Whenever we're using specific x values. And the graph of a piecewise function consists of several pieces, and we've already seen that. There's a bunch of pieces here, 4 pieces to be exact. We have our dot here, we have our horizontal segments here and here, and we have our other line segment, or our other line there that has a slope of 3. Now, can we use function notation to represent the parking situation from earlier? Actually, yes, we can. Here's a reminder of what that was all about. We have our graph and the corresponding word description there, and I'll show you what the equation for this piecewise function looks like, and then we'll analyze each piece separately. The first piece of our function here is f at x equals 0. And that only occurs when x equals 0. And you can see that right here. That's just this single point. When x is 0, we have a y value of 0. Then we get f at x equals 5, or you can think of it as y equals 5, when the x values are between 0 and 1. And that's from 0 up to and including 1. That's what we have here. Here we have y equals 5, just a horizontal line, from 0 to 1. It does not include the value at 0, but it does include the value at 1. Similarly, f at x equals $12.50 for x values from 1 to 2, not including the value at 1, but including the value at 2. And then this one might seem a little bit strange. F at x equals 3x plus 7, and you can think of that as y equals 3x plus 7 when the x values are greater than 2. And that's this part right here. Now perhaps some of that is a little easier to understand or easier to see than the other part. The 3 just relates to our rate of $3 per hour here. Okay? We can see that every time we go up 1 hour, we're rising $3 in total cost. But what's this 7? Well, remember, we want it so that at 2 hours, we're paying $13. And if we substitute 2 into this, we get 3 times 2, which is 6, plus 7, which gives us that $13. And then from there, we want to rise $3 for every hour. And a question I often get asked is, well, shouldn't this be 3x plus 13 because it kind of starts at a y value of 13? Keep in mind, this line doesn't actually start at a y value of 13. We get 13 when we sub in x equals 2. If we want to find its true start value, we need to trace it back to the y-axis. And if you do that here, remember we're at 13. So if we go back an hour, that'll bring us down to $10. And if we go back an hour, that'll bring us down to $7. That's the actual start value, the y-intercept. But keep in mind, we want it to be $13 when x is 2. So that's why we're using 3x plus 7. All right, so let's do some more examples here. First, we'll sketch the graph of the following piecewise function. We have f at x equals x squared, and that is what we use when the x values are less than 2. And we have our other piece, which is f at x equals 2x plus 3. That's what we'll use when the x values are greater than or equal to 2. So what does this look like on a graph? It looks like that. Notice we have our parabola here, y equals x squared, and you can draw that y equals x squared parabola the way you usually draw it. Okay, nothing special. The only difference is now we're going to stop it when we get to an x value of 2. We're just going to cut it off because this parabola is only used for x values that are less than 2. That's also why we have an open or a hollow dot here to indicate that that point that goes with an x value of 2 is not actually on the parabola. Then we switch to our function y equals 2x plus 3. And that's a line that has a y-intercept of 3 and a slope of 2. So if you wanted to draw that, normally we'd start at a y-intercept of 3, and our slope of 2 means we'd go over 1, up 2, over 1, up 2. You can see it hit the point there. Over 1, up 2, still on the line, over 1, up 2. The only thing we have to remember is we only draw this function for x values greater than or equal to 2, so we should not be seeing this line when the x values go below 2. We do have a solid dot here to indicate that the point corresponding to an x value of 2 is actually part of this piece of the graph here. Okay, so that's what it looks like. Notice we do have discontinuity. At x equals 2, we jump from the parabola here up 3 to the line here. That gap there means we have a discontinuity. So the graph or the function is discontinuous at x equals 2. All right, question number 2 here. Let's determine the algebraic representation of the following piecewise function. So we do have a piecewise function, and the first thing I'll draw your attention to is this curved part along with this curved part. Those two pieces are actually part of the same function, okay? And perhaps you remember that's the function y equals 1 over x. So we have y equals 1 over x here and here. That's all one function there. And then we switch to this. Now, what's the equation for this function? Well, it always has a y value of 2, so this is y equals 2. So sometimes we're using y equals 1 over x, and sometimes we're using y equals 2. When? Well, look at where it switches from the 1 over x function to y equals 2. That happens at an x value of 2, right here. And as long as we're below 2, or at 2, because of this solid dot, we're using 1 over x. And as soon as we start looking at x values above 2, we're using y equals 2. And that's why our equation is this. We have f at x equals 1 over x, or y equals 1 over x for x values that are 2 or less. And we have f at x equals 2, or y equals 2, for x values that are greater than 2. All right, and we'll finish with one more example, and this one I will actually write out here. The question is the following function continuous at the points where it is pieced together? Now take a look at this. We have a piecewise function here that has 3 pieces. We're using f at x equals x plus 1 sometimes when x is less than or equal to 0. We're using f at x equals 2x plus 1 when the x values are between 0 and 3. And we're using f at x equals 4 minus x squared when the x values are greater than or equal to 3. Now notice that each of those functions themselves are continuous. Each one is continuous. X plus 1 is just a line, so is 2x plus 1. There's no gaps or breaks or holes or anything like that there, so they're continuous. This here is just a parabola. You can think of it as y equals negative x squared plus 4 if that's easier to see, but parabolas are continuous as well. They don't have any gaps or breaks or holes or anything like that. So what's all this talk about discontinuity? Well, there is still a possibility of discontinuity with this function, and it would occur when we switch from using the graph of y equals x plus 1 to the graph of y equals 2x plus 1. Now, where does that happen? That happens at an x value of 0. This function is the one we use until we get to 0. Once we get to 0, we switch over to this function here. Now, the question is, does the end of this part and the beginning of this part line up? Do they overlap? Do they coincide? Or do we get that gap creating a discontinuity? And we can figure that out by figuring out what happens here and here at an x value of 0. Similarly, when we switch from this function to this function, we have to ask ourselves, do we have the situation where this function kind of stops at the same place this one starts? Or do we have a gap? Do we have a jump, which would be called a discontinuity? And that happens at an x value of 3. This function stops being used when we get to an x value of 3, and this one starts being used. So all we're going to do is figure out some y values. We're going to figure out the y value of this function and this function when x is 0. We're going to see if we get the same thing, because if we get the same thing, that means that those two pieces, one picks up where the other one leaves off. And if we get something different for that y value, that means we have a jump, which is a discontinuity. So let's start with that. We'll say at x equals 0. Let's take a look at these two functions here and see what we get. So for the first one, we have y equals x plus 1, which would be 0 plus 1, which is 1. For the second function, we have y equals 2x plus 1. So that's going to give us 2 times 0 plus 1, which is also 1. Notice these are the same. And what that means is when we switch from this function to this function, which happens at an x value of 0, our first function stops at a y value of 1, and our second function picks up at a y value of 1, right where the first function left off. So we're not going to have a discontinuity. The two graphs coincide. They line up at that point where x equals 0. So therefore, we can say continuous at x equals 0. Continuous at x equals 0. Let's just check where we switch from this piece to this piece now and see if we have a jump discontinuity there. At x equals 3, let's take a look what happens with our 2x plus 1 function and our 4 minus x squared function. We'll substitute in 3 for x this time because that's where we switch from this function to this function. It's at an x value of 3. 2 times 3 is 6 plus 1 is 7. And then 4 minus 3 squared is 4 minus 9, which is negative 5. Aha! Notice now, these y values are different. So what does that mean? Well, it means that this function, once it gets to an x value of 3, it stops at a y value of 7. And then our other function starts up there at an x value of 3, but it has a y value of negative 5. So it's starting lower than where that one stopped. And as a result, we have that gap in the graph. So we could say, therefore, discontinuous, continuous at x equals 3. All right, so is the following function continuous at the points where it's pieced together? It is not continuous at 3. We have that difference in y values there. And it is continuous at 0. And that's it. There you go.